In just a couple of months, Tesla's Robotaxi is about to revolutionize transportation as we know it. This will be a key part of Tesla's future vision with autonomy and the artificial intelligence that drives its full self-driving technology. Vehicles operating as autonomous robots will have a profound impact on society. Today, my guest Phil Beisel will break down this groundbreaking technology and explore the AI behind it. Phil was a founding member of the technical team at Rivian, an electric vehicle maker. Before Rivian, he held various engineering management roles at Apple. Welcome, Phil. Thank you for joining me again.
Hello, Herbert. We're back.
We're back. And, a lot of things that the question I keep getting from a lot of my audience is, we know that Tesla's ahead in terms of the neural nets and that, this requires machine learning and we're headed towards full self-driving. And now we're getting comparison with the Chinese. They're still using, the systems are still using the old technology of coded systems and LiDAR. What I wanted you to do today is break down the technology behind neural nets, why it's different from the LiDAR. So let's start with that. You've got this, you do these great articles, by the way. If people want to check them out, check out Phil's account at X at PBEISEL. He does these articles. This one here is the magic of Tesla FSD, and he breaks it down in detail. We'll go through that. You've got this page here. Tell me what we're going to be covering today, Phil.
Well, often we talk about FSD, and as I said, the magic of FSD isn't explored in depth. So I want to go a little bit deeper into the tech here, the neural net technology. What you saw on that slide was a representation that the perceived advantages and what I call compounding advantages are that Tesla has a large fleet of data collectors and it has a large compute center to train the models. But the question is, what is it doing? What is it doing? And we can compare that to others as you wish.
Yeah, sounds good. So I thought to put this in context, I'll share with you what these Chinese social media folks are, they're testing out the FSD there in China, and they're realizing that the real difference between FSD and, for example, Huawei, which many people before FSD was rolled out there, they thought that was the best intelligent driving system out there. We got a blogger here that explains the difference. And then I think from this, you can explain how Tesla's technology actually does differ. So this blogger and Chinese influencer named Andy Lee, he shared his insights into the realities of Chinese intelligent driving solutions, and it's critical. He's critical of their capabilities being overly exaggerated, right? To be fair, some of the issues of Chinese systems he describes are reminiscent of FSD. It's like what FSD was like in the early builds, version 10 and 11, from what he can see. So here's a translation. The guy says this: what consumers want is actually very simple. Do I want to use it or not? That's the only standard. If the steering wheel wobbles and the car sways, yeah, technically you don't need to take over, but do you dare to use it? The moment that happens, the user immediately switches to manual driving, curses idiot, and just drives themselves. When encountering a parked vehicle, right, Huawei systems and other Chinese intelligence systems, they don't go around. They just wait foolishly, then slowly signals and changes lane. Okay, sure, there's no takeovers needed, but tell me, would you be frustrated? At an intersection with no traffic light, these Chinese intelligence systems, they don't slow down. They just charge right through recklessly. Looks bold and efficient, but in reality, it's just plain stupid. Meanwhile, the driver is freaking out inside. There's so many issues like this, I could list a whole bunch, and none of these can be measured by some nonsense takeover rate. Real tech and capability are becoming more important than ever. The moment a user turns on intelligent driving, they immediately know if it's good or not. Does it feel safe? Is it reassuring? Is it actually usable? This is his blog post that he did. And I'll play a video, and I'll turn down the Chinese driver, but so we can read the actual comments a little bit better.
减速非常好，非常好啊！这个地方他妈经常有那些自动驾驶直接往前冲，他妈傻屌，真的。
Yeah, so let me. So there's a car on the right, a car on the right. I saw it ahead of time, slowed down, very good, really good. At this spot, some autonomous driving systems just charge straight ahead. That's dumb, dumbass. But he noticed that with driving, full self-driving, it recognizes what the scene is and it knows what to do instead. Yeah. What's your thoughts, Phil?
Well, I mean, this is where we are. What it is reminiscent of version 10, version 11, which what Tesla did was they made a magical shift in version 12, and they went to a pure end-to-end neural network. It's end-to-end AI. It made a huge difference because if you look at what's going on there, while in the Chinese system, the perception side might be a neural net. I just don't know the details. The decision making is a coded system, as far as I understand it, and that feels robotic, and probably always will feel robotic. If you look at what's happening, and we'll dive pretty deep into this with Tesla AI, what we're doing is we're selecting good driver scenarios, and the car drives exactly like a good driver would. In fact, with the neural net, it doesn't know how to deviate from that plan. So as long as Tesla selects, in this bell curve, we have data on the left that are terrible drivers, too slow, maybe too cautious. Data on the right that's too aggressive, also terrible drivers. Neither of those feel comfortable. You wouldn't want to be driving with folks that drive like on this side of the bell curve, this side. But in the middle, when you have good driving behavior, Tesla can select that and train the network on that. And that becomes essentially their secret sauce because it just simply mimics the best driving behavior. It's not the average driving behavior, it's the best driving behavior. So if you look at circumstances where you see a Tesla slow down, FSD slow down through an intersection, that's because all good drivers just simply do that. Or go around a car because all good drivers do that. So you end up with both a system that feels smooth and fluid and like the best driver you're with. And ultimately, it's safe too because the good drivers are safe drivers, right?
Yeah. This is the difference. I think people think, oh, Waymo's already solved full self-driving, autonomy. They've got cars, they got LiDAR.
No, it's different.
But what it can do is prevent an accident, but it doesn't mean it can drive it's not like a good driver. And it makes all the difference.
Yeah, so accepting this is based on having it feel very fluid, not just safe. Safe is super important, super, super important, of paramount importance, but this fluidity in the driving, to have a good driver drive you, to be in a car with somebody that you don't feel tense, you feel relaxed. That's what the outcome is going to be for Tesla because of the selection of the data that they use to train the model.
Yeah, I guess what I'm saying is that even with LiDAR, right, it says, oh, here's areas you don't want to hit it, but it's going to barrel through a intersection, which then puts you in an unsafe scenario.
Yeah,
right?
the LiDAR doesn't change. The LiDAR doesn't change this. The LiDAR is just another sensor modality that allows them to then code to that. But once they're coding to it, as opposed to using an AI system, now it just is going to feel robotic. There's no real way around that. It's hard to smooth that out, make it feel, and not only just feel like a great driver, but also make decisions like a great driver. Because there's just a huge tail of decisions out there that people make without thinking, and it's hard to code that into a decision tree that ever makes sense. I mean, Tesla tried. Version 11 was the last great version that tried that idea, and they discarded it because they couldn't see a path to convergence.
So this is very interesting. I'm very curious. Now I want to know, how does FSD's AI work? How does the neural nets? What makes it tick? All that. Tell me.
Yeah. So, I mean, this slide, what we're trying to convey here is that a lot of people have focused on the vehicle fleet having a lot of training data, super important. Focused on the compute side, look at that, the front end of Gigafactory. I mean, that's just massive in scale. You can't imagine another car company on planet Earth having this type of compute. But there's little focus on the actual workings of the AI, and in a sense, they're all interwoven. It's a compounding advantage. It's not that it's not one advantage drove the other. That's a good pun. But it's sort of like if you're gonna do the AI, you need a lot of data. If you're going to do the AI, you need a lot of compute. Tesla has the great advantage of having that fleet of, literally millions of vehicles on the road collecting data each and every day, like real world, literally real world, because it's exactly what it is. And of course, they built compute around this because they have, they realized they needed it. But then the question is, how does it work? So let's jump into it. Okay. So I think it's super important to describe the difference between the training and the inference. All right. Um, they are very different types of things. They use some of the same compute operations. But what training does is it builds a model. And training is done exclusively in the data center. That data center that I showed in the previous picture is known as Cortex. It has about 50,000 or 100,000 GPUs. And the whole purpose of training is to produce a model. And this occurs once per version, and it's a many, many week process. We don't know exactly how long, but it certainly could span 2 months of compute time. So it's a massive, massive process using many, many GPUs to create this one single thing called the model. And once we have the model makes its way to the car through an over-the-air update. And now we do a process called inference, where we are actually taking in pieces of driving data and determining how we actuate controls, accelerator, brake, steering. And this happens on the vehicle 15 to 30 times a second, all the time. It even happens when it's not engaged. So engaged is when you're using it, but it also operates in a shadow mode. So it can note the differences between the driver's behavior and the FSD's behavior, so it can use that to select pieces of data to send back for another training. So that's the big difference. I mean, that's the big setup here is you have training, you have inference. It's an asymmetric process, meaning training builds the model moves to the car. Once it moves to the car, it's read only. And then it's just pushing data through it at a very, very high rate to make the decisions that ultimately actuate the controls of the vehicle.
Okay, so this is how full self-driving AI works. How does it work if you have LiDAR combined with code?
Yeah, well, let's look at this slide in totality, and I'll answer your question, I promise. This is sort of a, if you will, kind of an architectural look at the neural network itself. And it shows the three major components: the input layer, the middle, which is the hidden layers, and then the output layer. Now, to answer your question before I get into it, is LiDAR would just be another input modality.
Yeah, just an extra
That's
one.
all.
Mm-hmm.
So in the case of Tesla FSD, camera data is visual data. The data from the cameras is the principal data. It's 99% of all the data that's used in the system for the inference and of course the training. And you've noticed I put this thing 8 times 3 times 12. What that's saying is that there's 8 cameras.
Gotcha.
They're grabbing about 3 frames of data through a time period. Think of this as a slice of time. Okay, you're driving a slice of time. How long is 3 frames of data? It could be 3/15ths of that second. Okay, a portion of a second.
Yeah.
1280 by 960 would be maybe the horizontal by vertical of the captured frame. All right, it could be bigger than that. And then 3 is the depth. 3 is like the red, green, blue value. Okay, I mean, the point I'm making here is if you multiply this together, you get a pretty large number, and that's happening in inference. 15, well, maybe about 15 times a second.
Yeah.
Possibly, you're pushing that kind of data through the system. And then you have some other data. Let's not forget that there's IMU GPS data. So IMU is the inertial management unit. That's where you're determining, you're able to pull through the roll, pitch, yaw of the vehicle and its forward acceleration. GPS, of course, latitude, longitude, altitude. And then we have some vehicle state data, which we'll come back to in a second. Audio data, that's a new thing that's coming, either released or coming soon. The purpose of audio data is principally to detect sirens from emergency vehicles, because it's not visual and you would hear it before you saw the visual. Or I should say, you would hear it before you saw the visual. That's the whole purpose of the siren, right? And so they intend to include that. And then context data is other things like the hour of the day. Is it dark? Is it light? Like a
Mm-hmm.
lightness value, ambient light. Is it raining? Is there fog? Things that would. So what's happening here is we're capturing a segment, a little slice of this data, maybe 15 times a second or 30 times a second, and we're passing it through. We're talking about inference here. We're passing it through our hidden layers. We're going to keep that opaque at the moment, and we're coming to an output. And what is the output? The principal part of the output is to determine the steering angle, the accelerator, and the brake, right? So steering angle would be some kind of radians. Accelerator would be like maybe a value 0 to 1. 0 is no accelerator pedal. 1 is fully depressed. 0.5 would be halfway. Brake, similar kind of thing. And then there's some other things like we know that FSD will use a blinker, so it's clearly indicating in its output to turn on the left blinker if it's going to move into a left-hand lane or take a left turn, et cetera. And we don't see the horn being used, but maybe that's a future output. So to zoom out on this picture here, what we're saying is we're taking this slice of input data, which is largely characterized by what I put here. Maybe there's some other pieces to it. We're pushing it through this model in a process called inference, and we're arriving at outputs which control the vehicle. And then we're rinse, washing, and repeating this continuously. And some of that data, or at least the outcome of that data and how the car is set up with its steering, accelerator, brake, comes back and comes through the input layer, because what we're trying to do is integrate a smoothness over time, right? We don't want to change a full acceleration to a full brake instantly. We have to integrate that over time for a smoothness.
Mm.
So that's sort of a bit of an opaque view of the model, but with the input layer and the output layer reasonably described. Here we're going to just dive a little bit deeper into this, and it looks maybe a bit intimidating, but it's worth teasing it apart a bit. I'm exposing now what I call the hidden layers, and what's happening here is that we have something in the hidden layers we call nodes or neurons. Again, neural network is sort of largely named, maybe symbolically, after the human brain with its neurons and synapses, connections. And so this computer construct known as a neural network sort of largely analogously operates sort of that way, although I think it operates differently, but it's at least analogous. And so that's why it's called a neural network. And what we're left with here is a set of connections between all of these little purple boxes that we call weights. And then each of them have what's called a bias. And you've heard people have said, okay, there's so many parameters, or there's parameters in a neural network. Parameters are a summation of the weights and biases. All right. Now, just to be very clear, each upstream node, each one of these little purple boxes, connects to every single downstream node through a weight. So there's a lot of connections. It's a fully connected network, which means that each one in one layer connects to every single one in the next layer, and so forth and so on. It has been said that version 13 of FSD contains about 1.5 billion parameters in total.
Yeah.
So you can think of the weights as about 10x more weights than biases, although that's not exactly true. But the weights far outweigh the biases in count. Yeah,
Okay.
in count. So this is what you have. And what we're going to do now is we're going to talk about a little bit about how this thing gets trained. But what I want to leave the viewer with is the idea that when you move this to the vehicle, all you're left with at the end of the day is the weights and the biases in the hidden layers of the network. Okay, inputs are going to come and outputs are going to come as part of the processing. So you don't have those layers are just architecturally there, but you're left with the weights and biases. And when it gets to the vehicle, those weights and biases are read only. There is no change to them. The car isn't improving its ability to drive people have often said, well, I go down the road and it does this on one day and then it does something on the next day and it made a better decision. Oh, it must be training. That's not what's happening. Training is all in the cloud and the compute is completely on the car and it's only read only. Now, why is that happening to that person? What they're not aware of is that there's probably some differences in actually what kind of visual data is there. There might be a car parked on the road on one day and there wasn't the next, and they didn't really notice that. They just saw the behavior of the car, but that was really important in the input part of this. Now, that is not to say that the future of FSD is completely a read-only model on the car. There may be some opportunities where the car builds up a bit of a training context, but that may not be changing the model itself, just more of the inputs to the model, if that makes sense.
No, this is great to know. This is great. 1.5 billion. So the more, the better. And then, so a lot of people are saying, hey, once Tesla solves autonomy, other car companies can just copy it and then just do it. Can you just copy all of these?
At the end of this
weights
presentation,
and-
at the end of this presentation, you'll be convinced you could copy it. But I've simplified this greatly. And I've talked about it in this presentation as a single neural network. In reality, it's probably many. They feed each other in unique ways. How they select the data is part of the secret sauce.
Yeah.
How do they select the best driving behavior? So there's a lot of, as I say, there's a lot of secret sauce in the details. And almost none of those details we can really get into here. Some of them I understand, and a lot of them I don't, because they're proprietary to Tesla, and that's what makes that they've hired great people that understand this, and they have years and years of experience where they've experimented with a lot of different ways of doing this. In the early days, they built a neural network purely for what's called the perception side of self-driving. This is pre-12, and it persists today. But what perception is really just basically understanding the environment around the car, all the objects, the moving and non-moving objects around the car, and labeling them appropriately. And that's where they, built up their experience in building neural nets. The identification of stop signs and other vehicles and pedestrians and so forth. But as they moved into 12, they went end to end. And what end to end meant is that they actually started doing the planning side. As we discussed before, we were talking about the Chinese FSD, and we said that it's probably a coded solution. And what that means is that the perception side is probably AI, but the planning side, the one that's doing the actual decisions on what it does, is probably a body of code. And that's what Tesla discarded after version 11. They decided it would not work. It would never be smooth, fluid, or safe. So this is the fun one. If you understand this, you understand neural networks. And I'll try to go through it. It's not that complicated. What happens here is that this is all about training and building the model. Okay. So what Tesla does is, as we described that input data before, we talked about video and sound. We talked about IMU and GPS and some vehicle state data and some context data. Imagine capturing that data and bringing it to Tesla's cloud, which they do, a lot of it, probably hundreds and hundreds of billions of samples that they've collected across the fleet. And they also do something special here where it's called labeled data. And this is very important. I don't go deep into this, but all of this type of artificial intelligence, all this neural network is called supervised. And what supervised means is that the input data and its output are labeled. In other words, they're known. And let me give an example. I think this will make this discussion easier. Imagine that I select a set of maybe 100,000, 200,000 driving samples, driving input data, and it's all about stopping distance to the vehicle in front of me. Okay, so there are times when the vehicle in front of you will stop casually, and you slow down, or the FSD slows down appropriately, keeps a good standoff distance to the car. There are other times where the car in front of you will stop short, if you will, and then you're trying to avoid the rear end
Mm.
collision. So there's a hard brake that occurs. Um, so imagine that we are in a condition where we have a couple 100,000 samples that correctly tell us that from this input data, in other words, we're at this distance from the car, we're moving at this rate. Remember, we have frames. So frames allow us to show the frames of the video, allow us to show difference of time. So we can see our movement, right? And each of those 100,000 or so samples that I mentioned have a proper output labeled for them. Okay. In other words, it says brake at 62%. Remove accelerator, steer straight, brake at 62% for this one. And what would that yield? That would yield Tesla would stop behind that car at a safe distance. And maybe another one says brake at 74%, and it would yield the same result, right? And you would have none of them that would say brake at this percent and the collision would occur, right? Because that's what we're trying to avoid. So we have good driving samples and we labeled the outputs. Now, what's happening here? Let's imagine a couple 100,000 examples of that, and we'll call that batch one. So what training does is it runs in a series of what's called epochs, and just think of them as cycles. And the idea is that we take a bunch of data, and there's a lot. I mean, to say 100,000 samples, that's not even close. I mean, we've got a couple 100 million, billions, and the high billions. I don't know what they're using to train the model, but it's a lot. And so an epoch is a cycle where they take all the training data and they flush it through this system to train the model. Okay. But it's broken up in batches. So let's assume we're talking about the batch that I mentioned before, the 100,000 good standoff distance stopping, right? And what we do is we take that data and we push it through this model. And what we're doing there are two passes. The data goes from the top down, from the input to the output side, through all those hidden layers, no matter how many there are. And that's called the forward pass. Okay. And things occur during that forward pass. And what it does is each time it goes from one hidden layer to the next, it runs a bunch of things called activations. We don't need to detail what they are, but they're functions that allow the network to technically create a nonlinearity. In other words, it creates this nice smoothness to the data. And when we get to the end of that batch, so again, we have 100,000 samples, standoff distance, we've run them through, we calculate something called a loss. So one of the principal things about a neural network is to calculate this concept of loss. And what loss is, in simple terms, is it's the difference between what we need to have happen and what actually the network tells us is happening. So let me give you an example. Imagine that we take our training set, 100,000, and we run it through, and we find out that our loss, or that our braking, the average braking across these 100,000 samples, the output says brake at 50%. But it's not good enough. We have to brake at 75%. If we don't brake at 75%, we don't depress the brake at 75%, we're going to hit the car in front of us. All right. So the loss is the delta between the computed 50% and the 75%. So then the network, having that loss, basically what we're saying is we need 50% more braking power, or we're going to hit the car. Having that loss, we do this magical step called backpropagation. So if you remember two things about neural network training, the loss and backpropagation, you basically get the idea. What happens in backpropagation is we walk from the output side back towards the input side. We walk backwards through the network and we adjust all the weights and biases so they give us a smaller loss. Okay. It may not reach that 75% braking. Maybe it comes down and says, oh, well, it was outputting 50% and now it's 71% braking. But we've reduced the loss significantly by pushing the data back through the network, adjusting those weights and biases. Now, am I going to tell you what's in the loss function and how back propagation does that? No, there's a lot to that. It's not heavy math. There's a lot of calculus in the back propagation. But ultimately, what the takeaway here is that we have data that tells us the answer. We have data, it's labeled, it has the answer. All we're trying to do is build weights and biases so that they give us as close approximation to that answer as possible. Okay? Why? Because at the end of running an epic through the system, the whole training set, we can then use a data set called a validation set. This is unseen data, so it was not used in the training.
Mhm.
It's new data. We've also labeled that data. We know what its outcome has to be, and we can see whether we're converging or removing loss. What we do then is we repeat this process over and over again. And as back propagation occurs, those weights and biases get nudged. So as you remember, I said 2 slides ago or a slide ago, it was like 1.5 billion parameters, 1.5 billion weights and biases. They are a set of numbers, okay? Somehow those numbers through this process get trained such that they minimize the loss. So what does that mean in real world? It means this: when you're now running inference on the car, you're in the car and it's taking data at 15 times a second and it's pushing it through the system and it's coming up with a set of outputs. And those outputs say the accelerator pedal should be at this, and braking should be at this, and steering angle should look like this. Those things have been trained on this data. The loss is quite minimal. Okay, we've trained it through these epics, constantly pushing the data through the system until the loss starts going in the wrong direction, and then we stop. So how somebody say, well, how many epics would you have? You have as many epics as necessary to massage that set of parameters to where the loss is minimized. Okay, and what Tesla is doing is they are running an enormous validation data set through. So before that model ever ends up on a car, they already know how it's going to perform.
Mhm.
And it has no chance of performing differently than that on unseen data, right? In other words, if the unseen data set is large enough, it statistically represents literally every potential driving scenario. Now, one might say, well, there's a long tail of driving scenarios. There is. Tesla continually is training on more and more scenarios to minimize the loss with that trained data. So, what are the takeaways? The takeaways are that we have this thing called a neural network. It is a big, big box of magic numbers, but the distillation of what those numbers are comes through this training process exclusively. All right. And we are simply trying to eliminate the loss in each step from what is the perfect outcome to the outcome that the data is showing us. And as we massage those numbers and we bring that data through the system, the loss gets smaller and smaller and smaller. And it's very measurable. It's very measurable. So that means that, as I said, before the model goes out to the public, before it's ever utilized, it's run through an enormous validation step, and they know how it's going to perform. It's empirical.
Mhm.
So that's sort of what's going on here.
Yeah, that's great. Yeah, that explains a lot, actually. I love this. So the more batches you have, the more likely you're going to have enough data set to run through the model. And then it's self-learning, right? Because it's what you've explained here. Loss is calculated, back propagation keeps self-learning, and then you run it through a validation data set to see how well this new model performs.
Yeah.
So
And
it's always getting better. Yeah.
remember what we are doing is we are selecting good driving scenarios. from your best drivers, both from a safety and fluidity of drive kind of decisions they would make, and we're codifying them in this box of numbers. That's what's happening. And so now, if we're good at selecting our training data, which I guarantee Tesla is very good, and there's a lot of secret sauce there, and how do they select that training data?
Mm-hmm.
I'd say there's more magic than that in that than anything I've described thus far. If they're good at selecting that training data, the outcomes and how the car drives are kind of known before the car ever hits the road.
Yeah.
And that's the thing that I think people misunderstand about full self-driving is it's not each scenario is not new at all. It's already known. There are scenarios that aren't known, but those scenarios end up as interventions or deviations from what the driver does in the shadow mode. And then they select that data and they run it through some process that validates that they want this piece of selected data, what they want the outcome of that piece of data to be. And then they put it in the training set.
Mm. Great explanation. I hadn't understand this a lot more clear. This is good. This explains why more data matters, why it's important.
Typically more data matters. The only issue here is there are ways that you can overtrain a network. People call it overfitting, and that it becomes tuned to only the data that has been seen and not the data that is unseen. Because remember, what's happening here is all the decisions in your car are made on unseen data. None of the data that your car is making decisions on 15 times a second has anything to do, is not a piece of train data. The train data is sort of the sort of prototype for that decision, if you will.
Yeah.
So if you were to overtrain the data, then you might end up with a neural network that is only good on the train data and doesn't work on the unseen data. But the unseen data is where it's at. That's where your car is actually operating.
And this is why maybe Waymo can do very, very well in these various grid city blocks, well-defined blocks. It can do really well in those ones. But you take it out to any other place and it may not do well at all. Doesn't know what to do.
There's a lot of differences in how Waymo operates. Obviously, we know they use LiDAR. We know that they are largely attempting to map cities and match to mapping. So they want to, Tesla is this idea that you can take the car anywhere on any piece of data unseen. Remember, that's what we're talking about. And have the car drive as long as it's been trained on like scenarios. Like, for example, if it were to come across, say, what do we call those? Circles, rotaries, they've seen, or you see a lot of those in various areas, especially in the, what's that? Roundabouts. Yeah. Circles, rotaries, roundabouts. And if it's never been trained on anything like that, it might not know what to do. I mean, obviously, we have to realize that it's training on small slices of data, not big scenarios. It's not training on how do you work through a roundabout specifically, but it is training on potentially data that would be cars entering the road at kind of odd angles, and that it's angling around this thing and taking exit and so forth. So it needs to be trained on driving scenario. Like it couldn't know circumstances on a German highway unless it was trained for that data. But where there's similarities, it will operate just fine. Right?
I mean, if it can read a sign and if it sees that sign, it recognizes it before, understands the context. Maybe that's how, just like me, if I drove someplace, never seen a roundabout in my life, or how you go, sometimes you go to a different place and they have a different rule and different roundabouts, totally different, expectations of the driver. Would I be able to do it? Well, if I can read the signs, I might be able to. I can.
The Tesla FSD system will be best to adapt, the best adaptive system to roads it's never seen before.
Exactly. Yep.
And situations it's never seen before. However, it needs a lot of data. The good news is it has a lot of data.
It has a lot.
There's no miss here, right? In other words, that they're bringing in so much data that deals with scenarios. You notice that they talked about they wanted to train the model for the roads in China. And so what they did was they captured that they couldn't they can't operate the training component in a Chinese data center, and they don't want it to deviate from the US data set, right? They kind of want one data set across all this. They want to build one universal model, is a good way of saying it. They're not trying to build a model for China and a model for the US. They're building one universal model. It's called the driving model. Drives on roads anywhere. They couldn't gather real samples. But what they do have as part of their secret sauce is they have this incredible simulator. And they've talked about that in several AI days. And the simulator allows them to take scenarios and map them out to roadways. In other words, they see something in that YouTube video, and then they could probably take that video in of a intersection in China, in Shanghai or whatever, and map it in their simulator. And once they have it mapped in their simulator, now they can run a simulation, capture simulated data of that, and then include it in the training set. So yeah.
Sounds good. Okay, great explanation. Why data matters, how neural nets work. What's this convergence?
Well, this is sort of the end of the presentation. And what I call is FSD convergence. And what I'm trying to explain here is that what's left here is essentially to get to full self-driving. What is really full self-driving? It's unsupervised, right? That's definitionally what's required for Robotaxi. And that is when they've reached the endpoint here. To get there, I mean, they're on the march, what we call the March of Nines. They're improving the system by some decimal degree of nines, probably every major release or subsequent point release. And this is becoming nothing more than a compute-bound problem. Okay, that's my point. If you look at the little graphs at the bottom, you can see that what does it take to train one of these things? Well, on the vertical axis, we have compute time. And on the horizontal axis, we have parameters, the number of parameters of the network. So what do we know? We know that Tesla has told us that version 13 has about 3 times the number of parameters that version 12 has, right? And in sense, if everything else is held constant, that's about 3x the compute time. And what that means is it's literally if it took, say, 3 weeks to train version 12, it would take, using, holding everything constant, it would take 9 weeks to train version 13, right? If you look at data, that sort of has another sort of linear relationship. You have 100,000 samples and you double it. It essentially doubles the training time required to push the data through in its batches and epochs. It's a little bit more vertical because, anyway, ultimately, if you add the parameters and the data together, now what you have is a larger increase in compute time. So what Tesla is doing continuously here is they're increasing the size of their Cortex data center, right? So if they go from, it's been told to us that they had about 50,000 GPUs for version 13. If they were to double the parameters for version 14, but they also doubled the GPUs to 100,000, then it would take largely the same amount of time. And so what I call this is it is literally classically a compute-bound problem. It is solution to their problem is simply a matter of the compute. Now, one might argue they need a lot of driving scenarios, but there's infinite driving scenarios for them to select, and they get more every day, right? They had about 5,000 cars on the road a day running in shadow mode. They have plenty of data collection to run through this training process. So will they increase the model size? I mean, sometimes you would say the bigger the model size, the better. The more parameters in the network, the better. It's sort of true. But ultimately, the problem there is that then they run into a problem where the car's inference can't compute it. In other words, it starts to lag. They can't run it, like they're trying to run it 15 times a second, and it takes more than that to get through a sample, to get the properable the output they're looking for. Let's say it adds 30%, then they're going to end up having this latency, and they can't do that. So ultimately, there is optimizations they make on a continuous basis. It's a little bit more advanced than this conversation and how they do those optimizations. But ultimately, what they're probably doing more than anything right now is adding more driving scenarios into the training. And they're probably, version 14 is an increase in parameters, but probably not 3x, I would say.
Yeah, so Elon just confirmed, or he retweeted a post that said that, first of all, Tesla is on track to get 7 billion miles of full self-driving miles by the end of this year.
Yeah.
So they have enough miles, and then they're gonna the compute time is a real thing. It's time, and either you're going to take a year to get to the same place, or if you increase the cortex and grow that, then you can cut it in half, get the more fast. So the speed by which you implement compute data cuts how soon you will hit these March of Nines, and that's the game. And
it's just literally compute bound.
And so then if another company said that we're going to do this, well, can you build a supercomputer as fast as Tesla can, or how fast can you do it? It might take you a year, 2 years, 3 years to catch up if you have the data, and you have to build a supercomputer. That's the thing that people just haven't figured out. It's like, oh, Mercedes will catch up, and BYD will catch up. Well, show me their supercomputer. Show me their... Yeah.
Exactly, Herbert. I think if you think about it, can you name one single car company? I mean, we can't know this, but can we name a single car company that we would hypothecate has a tenth of the compute that Tesla has right now?
They're partnering with NVIDIA, and NVIDIA is saying, "Hey, I've got this, and you partner with me, and we'll do all."
Fair enough. I mean, what NVIDIA has said sort of is, we can give you compute.
You buy it from me. Not just a customer, really.
We can give you simulated data is another part of the story. I think there are things here. That's not falsehoods; those are real things. But I think if you go back to my first slide, it says the compounding advantages. A lot of people are focused on compute and data.
Yeah.
But what I'm saying is that while we described largely how this thing works, the FSD internally and how they've architected that AI is very proprietary to Tesla. And there is a lot of secret sauce. And I think part of that is data selection, and part of that is the neural networks architecture, right? And data selection is a big part of this, because they need to label data, which means that they need to take driving scenarios and figure out what the proper outcomes are. And they probably are doing that by a process called auto labeling, which is, in other words, what I'm saying is there's a huge amount of compute dedicated to just taking driving samples and getting them set with their potential proper outcomes and validating the proper outcomes and using them as selectable pieces of data.
Yeah.
So it is a compounding thing, right? If you have a lot of data coming in, remember, we talk about what did you say, 7 million miles on billion? Okay, but that pales into comparison the number of potential data selections they have through running it in shadow mode.
Exactly.
Because
they've
that's
been doing for decades. A decade.
That's the fleet. That's the fleet. Every car running down the road that is a Tesla is operating in shadow mode, or potentially operating in shadow mode, which means that they're collecting data regardless of whether FSD is engaged for the purpose of driving the vehicle or not. Right? And then Tesla gets to decide, let's call it their high quality problem, which of that data is worth the expense to move and store in the Tesla cloud, because remember, they have to move it off your vehicle. They probably do that largely through Wi-Fi in your garage in the evening. They probably don't use the cellular link for much of that because it's very expensive. And they have to decide, is this piece of data worth it? Um, and then they bring it to the data center, and then it has to be stored. Then they have to take that data and they have to label it with the proper desired outcome from the the scenarios that they're pushing it through, and then they use it as part of their training set. And
Yeah,
all of that is a lot,
it's a lot.
right? Yeah.
Okay. Fantastic. Thank you so much for teaching us everything about how FSD AI works. You do a great job of explaining things, and it was very cool that you explained all the inputs that can come in. It was very complete, and then of course the outputs, and then all these little weights of how much what to do, and basically everything that comes in is unseen data, right? So even if I drive
Right.
the exact same road that you do,
It's unseen
I
data.
might it's not going to be the same data because the sun might be slightly different that moment versus
Yeah.
your moment. The
Yep.
wind will be, all these little things.
Yep.
But you did a great job. I suggest everybody, go to X, sign up and subscribe to Phil, Pbeisel. He's got these articles. He always does deep dive articles, and
Yeah.
this is the latest
Two
one.
This process I describe in two articles: the magic of FSD and the magic of FSD part two.
Too, yeah.
Today was more on the part two. It's a bit of a deeper dive.
Mhm.
And then the other article to look at is the accelerated computing, because it really kind of um, takes the veil off of what's actually happening in the data center
Yeah,
and how you train these models, in terms of like all the matrix multiply operations that occur. Like why is it that we need GPUs? What do they do? What is the parallelism all about? One of the parts that's not described here is all of how we coordinate these incredibly large clusters of computers. I think Elon described that as a symphony, where he said the symphony comes up. I mean, remember he was talking, people might
yeah,
remember this, he was talking about the Memphis data center for training the model for Grok, the LM model, which is, a similar, it's also a neural network. And he said that they had power problems because because the way it would work like a symphony is it would come up and it would deplete, and it would do this in cycles. And what's the part of the magic of what Tesla has done that isn't just out of the box is that they've created this cluster, and the cluster allows them to take these batches. I when I talk about these batches, I'm not talking about a single computer. I'm talking about spreading these batches out
yeah,
through this whole parallel network and keeping ultimately a synchronized model that has to be the outcome model, right? So you can imagine what that's like in terms of the not just the compute, but all the network activity required to coordinate and synchronize the computers together.
yeah,
And they do, as you could see, remember I said, if you look at batches and epics, if you look at that concept of an epic, the epic is sort of like part of that symphony where it comes up, it runs the data through, and then it depletes and it starts a new cycle. And that depletion, or that point where it goes to zero, meaning the compute is not live and happening, is because basically at that point you have all this IO where it's moving the data and synchronizing the data back to the common model through the network. So now you go from compute bound to network bound and back and forth. And
hmm,
it's quite a thing to pull that together in a data center like that, and also
yeah,
deal with the resiliency of potential failures, right? Because you're operating this thing as a collective. If something falls down, how do you deal with that? And these failures happen because if you there's a certain amount of failure that occurs, and you have to be ready for that failure to occur in that network. So
yeah.
it's really quite extraordinary what they've
Yeah.
done.
Software expertise, hardware expertise,
Mhm.
networking expertise. Big. I think at some point, even the big Mag 7 guys, all the top experts, said that 30,000 GPUs clustered together was a limiting step. They couldn't get past that.
Yeah,
Elon
it's
comes out, figures out how to do 100,000, and they're all shocked because they thought it was impossible to do anything past 30,000.
it gets really, really hard. And Do you recall that Elon said that they're moving the XAI data center up to 1 million GPUs, right?
Yeah.
And the whole point is to have these things operate. If you look at that last slide where I talk about FSD convergence and that it's largely a compute bound problem, they want to have more compute.
Yeah.
And so what they need is they need that compute to be as efficient as possible. In
And
a
it's
sense,
time.
they want, they want
Because
it
if
to
you've got
be
the big compute, then you can do things half the time, one-tenth the time.
half the
that
time,
other people
twice
can
the
do.
data,
Yeah.
larger models. I mean, you get to move the levers.
And that speed, that's exponential curve, which means that you will grow faster and no one can catch up to you.
That's also
none of your competitors can catch up to you.
That's also an outcome, right?
If you keep getting there faster than everyone else and getting bigger. So
yeah.
Okay.
I mean, right now the state of the art is to train a neural network, and it becomes a compute bound problem that in its extreme. And because of that, you get great advantage if you build that large cluster. So it means that the capital required to do that is enormous.
Yep.
The expertise that you need to bring to bear is enormous. Like, it's hard for me to believe that your ordinary car company knows how to build these clusters, right?
Yeah, they can.
It's just a different thing. And then, you have that additive to the data component, and assuming that the art is still the neural network, which I perceive that it will be for a very long time, meaning there isn't another approach, if you will. I mean, I think what we'll see from an approach change is we'll start to see some local context or local augmentation of the model that will deal with very specific behaviors that you need with your car. A good example is in my community, which is a gated community where I live, the residents have to take the right side. The Tesla FSD doesn't know that. It has no idea that my car is a resident car versus a guest car. It has no idea about that. And I can't teach it, right? FSD does not allow me to do the model's read only. I can't tell it.
Well, it's going to have memory soon. And I think once it has memory, then it'll memorize
that's
that in
largely
your specific GPS location, it does this.
That's largely the concept of context, right?
Yeah.
LMs do that. If you've ever had a conversation in an LM and you start talking about, a health problem, and then you bring something up a half an hour later and it says, and it has all that context, it's because what it's doing is it's just running the previous stuff through and marking it as context.
Yeah.
And if you looked at my diagram, there is this section called context, which I kept super small and said it's about things like the hour, the brightness, the time of day, but it can have a lot more there. So,
okay. Thank you very much, Phil. Another great show. Follow him and check out his website, or he has actually a website, right? And you also have
just X. Account. I just hang out on X.
Cool. Thank you, Phil. Talk to you soon.
All right.
Bye, everybody.
Yeah.
I've created a website that is the most comprehensive resource for the Tesla investor. Please check it out. Simply go to my website at herbertong.com.